All right. So by combining these two methods, we can start doing general unconstrained optimization. So the general unconstrained optimization, the fundamental idea is to approximate locally the landscape of the objective function as if it is a quadratic function. All right. So now, if we can, let's say, if we have a general function with a contour being like this hot dog shape. All right, and this function has, let's say, a local minimum over here. Cool. Then, because we don't know where the optimum is in the beginning, we choose a initial design. So let's say this is our initial design. So on this initial design, we can compute the objective function, right? So that's our x0. We can compute jx0. We can compute the partial derivative of jx0, j with respect to x, with respect to, let's say, s0. Sorry, let's say s is our design parameter. And we can compute the second derivative at the s0. So with these three, again, we can approximate locally what the landscape is using Taylor series analysis. Kind of a recurrent theme in this course is that if we have these three, we can approximate j of s as j of s0 plus we call the gradient dot with s minus s0, right? The linear term plus half of s minus s0 transpose times the Hessing, which is basically a high dimensional second order derivative times s minus s0. So this is the quadratic term in the Taylor series analysis. And of course, you can add more and more, and it becomes more and more difficult to represent it in a vector space. But we're going to stop here because we know how to solve quadratic optimization problems. All right. So now we have this approximate objective function being quadratic, and we know how to solve quadratic optimization problems. So what we are going to do is we are going to optimize this approximate function. So let's say the quadratic is going to give me, I have the same contour. If I continue as an ellipse, I'm going to have a quadratic function like this, right? Okay, so the minimum is over here. That means I want to take a step over here, right? Well, not necessarily that's always a good idea. Because again, this is a multi-dimensional problem, but I may encounter the same problem as in the one-dimensional problem, right? The gradient here might be relatively, the gradient may not be small, but the Hessing here, the second order derivative at this point, if it's small, then that is going to promote me to take an infinitely large step. Well, in multi-dimensional space is actually worse. It's not, my second derivative doesn't even have to be small. Only if a particular eigenvalue is small, I'm basically going to be messed up. So the recipe is the following. I'm going to choose this, I'm going to use the solution of this local quadratic optimization only as a direction. So I'm going to look at the next point as a direction to go in the high dimensional space. And I'm going to look over this line, right? The direction reduces the high dimensional optimization problem into a one-dimensional optimization problem. So let's imagine my S, so by minimizing this approximate quadratic function, I get a S1 tilde. S1 tilde is argmin over S of this JS0 plus gradient linear term plus the quadratic term that gives me that results from the Hessian. All right. So then what I'm going to do is I'm going to find through line search, okay, what is my actual S1? My S1 is going to be my S0 plus S1 minus S0, which is the direction, times a scaling factor, and the scaling factor, let's say delta, and the delta actually minimizes the J at S1.